Welcome to the All Sorts podcast. We believe curiosity. Well, it's your most powerful telescope, really. It brings the universe right into focus for you. Have you ever looked up at the night sky, all those stars, and just wished you could capture it?
That feeling, yeah, the sheer scale of it all.
Exactly. And imagine the phone in your hand right now could actually unlock some of those cosmic secrets.
It sounds almost like science fiction, doesn't it? But it's becoming reality.
It really is. So if that idea sparks something in you, you're definitely in the right place. And hey, while you're settling in, maybe check out our All Sorts Podcast YouTube channel. Give us a like if you enjoy this. Share it with anyone else who loves space or is just curious. And please subscribe so you don't miss what's coming next.
And we do have quite a back catalog now, lots of other deep dives to explore.
We do. Definitely browse through those. And you can find us on X, Instagram, and Threads, too. We love connecting with everyone.
So today we're charting a course towards something pretty accessible, I think. Smartphone astrophotography. And this whole idea of mobile observatories.
Ah, right. We're going to break down how your everyday phone, maybe with a few simple tricks and sometimes some pretty basic gear, can become this amazing portal to the cosmos.
Think of it as, getting really clued into astrophotography without all the intimidating jargon.
Exactly, making it approachable.
And the range of things you can actually see and capture is, it's kind of mind-blowing. We're talking the moon, planets, sure, but also things like nebulae, star clusters.
Even satellites streaking across the sky. Or auroras.
Yeah, even those fleeting moments. It's all based on the stuff we've been digging into.
Okay, so let's maybe step back a bit first.
Yeah.
How did amateur astrophotography even begin? It wasn't always just grabbing your phone, was it?
Oh, definitely not. It's pretty humbling to think about those early pioneers, people like Andrew Common back in the late 1800s.
Right, the British engineer.
Yeah, he was building his own telescopes, bigger and bigger ones, just trying to capture decent images on photographic plates. His photos of the Orion Nebula back then were apparently groundbreaking.
Wow. Competing with the pros even then.
Pretty much.
Yeah.
But it wasn't just individuals. You had magazines popping up like Popular Astronomy way back in 1893.
And Sky and Telescope later on in the 40s.
Exactly. They really helped build a community, share knowledge. I think the first mention in Popular Astronomy was this article called Astronomy with a Small Camera. Sort of quaint now.
Hey, yeah. Just a small camera.
But you see this shift, right? First, it was all about building the telescopes themselves. Then as cameras got better, people started wanting to, actually record what they were seeing.
And then the big leap came relatively recently.
Yeah, really post 2015 or so. That's when smartphones started getting cameras that were genuinely good in low light. Suddenly, almost any phone from the last, say, decade could take pretty decent shots of the moon, planets, star clusters.
Which brings us neatly to the smartphone itself, the tool we all carry. It's easy to forget how powerful these little cameras have become, especially for night sky stuff.
It really is. The low-light capability is key. Even without a telescope, just the phone itself, you can get surprisingly good images of the moon, bright planets, even some constellations pretty clearly.
So how does that actually work, the light gathering? Let's break down the basics. Aperture size, right? That's like the opening.
Yeah, think of it like a bucket, as one source put it. A bigger aperture, a bigger bucket, catches more light falling onto the sensor. Simple as that.
Okay, bigger bucket, more light. Then there's exposure time.
Right. It's just how long you leave the shutter open, letting that light hit the sensor. Longer time means you capture fainter things.
Makes sense. And ISO. That one's a bit confusing sometimes. It's not quite sensitivity, is it?
Not exactly, no. It's not the inherent sensitivity, what scientists call quantum efficiency, or QE. It's more like an electronic boost, an amplification after the light's been collected.
Like turning up the volume.
Pretty much. It makes the faint signal louder, but it can also amplify the noise along with it, so there's a trade-off.
Got it. So aperture and exposure gather the light. ISO boosts the signal. How do we get color, though, from these tiny sensors?
Right, good question. Most phone cameras use something called a Bayer filter array. It's basically a tiny grid of red, green, and blue filters sitting over the pixels.
So each pixel only sees one color?
Initially, yes.
Yeah.
It only records the brightness of light passing through its specific little filter. Then the phone's software does this clever trick called demosaicing.
Demosaicing.
Yeah, it looks at the color data from neighboring pixels and makes a really educated guess about the full color for each pixel. It's like filling in the gaps using algorithms, sort of like pointillism maybe. The dots blend together.
That's pretty smart. Now, phones have front and back cameras. For astrophotography, does it matter which one we use?
Oh, definitely. The back camera, the main one, is almost always way better. higher quality sensor, better in low light. The front one is really just for selfies and video calls.
Okay, so stick to the back camera. Got it. All right. Phone in hand, using the back camera. What else do we really need to get started? Do we need to rush out and buy a telescope?
No, absolutely not. For a lot of basic stuff, especially starting out, the most important thing is just stability. A tripod.
Ah, yes, the enemy of blurry photos.
Exactly. It's crucial for those longer exposures you need for stars.
Yeah.
And you'll need a little adapter, just a clamp really, to hold the phone securely on the tripod.
Simple enough. Tripod and adapter. What else is useful but maybe still pretty affordable?
Well, you could try using binoculars.
Yeah.
You can get clamps that hold binoculars steady on a tripod. That gives you much better views.
Right, steadier than hand holding them.
Definitely. And there are even adapters that let you attach your phone camera to one of the binocular eyepieces.
Oh, really? So the binoculars become like a zoom lens for the phone?
Kinda, yeah. A
Right.
telephoto lens effect. It really opens things up before you even think about a dedicated telescope.
That's clever. Okay, but what if someone does have a telescope or is thinking about getting one, like a bigger amateur one?
Then the smartphone becomes an even more powerful tool. You can attach it to the telescope's eyepiece with another type of adapter.
So you're using the telescope's light gathering and magnification?
Precisely. And if the telescope has a good mount, maybe an equatorial mount that tracks the stars as the Earth rotates.
Like with a clock drive?
Yeah, those are great for longer exposures. You can get really detailed shots of the moon, planets, maybe even some brighter nebulae or clusters that way.
Okay, but there's a big elephant in the room for many people, especially in cities. Light pollution. That orange glow, it washes everything out, doesn't it?
It's a huge challenge, no doubt about it. The sources we looked at had these light pollution maps, and yeah, especially on the coast, it's pretty bad.
So is smartphone astrophotography even possible in those areas?
It's tougher, but not impossible. And sometimes just driving an hour or two away from the city center can make a massive difference. You'd be surprised how much darker it can get relatively nearby.
So seeking out darker skies is worth it. Is there a way to measure how bad the light pollution is?
Yeah, there are tools for that, like the Unihedron Sky Quality Meter. It's a little handheld gadget that gives you a reading of the sky brightness. Helps you compare different spots.
Useful. But if you are stuck in the city, what can you realistically photograph? Is it hopeless?
Not at all. The moon is always a great target. It's so bright it cuts through a lot of the light pollution, especially if you're viewing it through a telescope.
Okay.
And the brighter planets, too.
Yeah.
You still have a lot of fun with those, even from urban or suburban skies.
All right, so we've got the gear, we've thought about location, now the techniques. How do we actually take these pictures? Where's the best place to start?
I'd say the easiest entry point is wide-field star photography.
Yeah.
Just capturing constellations, maybe a sweep of the Milky Way.
And for that, it's just the phone on the tripod again.
Pretty much, yeah. Phone, tripod, adapter. The key settings to play with are, first, use a timer delay, like 5 seconds, so you don't shake the phone when you press the button.
Right, avoids the jitters. And exposure.
Maybe start around 10 seconds, see what you get. Longer exposures capture fainter stars, but then you start seeing star trails because the Earth is rotating.
Ah, yeah, the stars look like little streaks instead of points. You want to avoid that for now, usually.
Generally, yeah, for a static star field shot.
Okay. Now, I've heard about things like bias frames, dark frames, flat fields. Sounds complicated. What are those about?
Ah, right. Image calibration. It sounds technical, but it's really important for getting clean, accurate images, especially when you do longer exposures or stacking. Think of them as subtracting the camera's own noise and imperfections.
Okay, break it down. Bias frames.
Bias frames are super short exposures, fast as possible, with the lens cap on. They capture the baseline electronic noise, the sort of read noise pattern the sensor always has.
Got it. The sensor's electronic signature, dark frames.
Also lens cap on, but taken at the same exposure time and ideally the same temperature as your actual photos, your life frames. These capture dark current. Yeah, it's like stray electrons that build up in the pixels over time, even with no light. Causes noise, hot pixels, those annoying bright dots. Dark frames help you subtract that out.
Okay, so bias for read noise, darks for dark current, and hot pixels. What about flat frames?
Flats correct for unevenness across the sensor. Pixels aren't all perfectly identical in sensitivity. Plus, you might have dust spots on the sensor or lens or vignetting where the edges of the photo are darker.
Ah, so flats deal with dust and uneven lighting. How do you take those?
You shoot a uniformly lit surface, like a white t-shirt stretched over the lens, pointed at an even light source, or even the twilight sky sometimes works.
Okay, so you collect all these different frames. How do you actually use them?
Well, there's a basic formula. Essentially, you subtract the master dark frame, which incorporates the bias, from your actual sky photo, the light frame. You also subtract it from the flat frame. Then you divide the corrected sky photo by the corrected flat frame.
Whoa, okay, that sounds like math.
It is, but thankfully, there's software for this. Programs like Deep Sky Stacker, which is free for computers, handle all this pre-processing.
What does the software do exactly?
It aligns all your images perfectly. That's called registration. Then it stacks them, meaning it combines them. And it applies the calibration, frames the darks, flats, bias automatically.
Stacking, we mentioned that. Why is stacking multiple photos so important?
It's all about noise reduction. Random noise, the sort of graininess you see, tends to cancel itself out when you average many images together. There's this thing called the square root law. Basically, if you stack n images, the noise reduces by the square root of n. So stacking 16 images cuts the noise down to a quarter of what it was in a single shot.
Wow. Okay, so that's how you reveal faint details. They add up, but the noise averages out.
Exactly. A faint nebula might be lost in the noise of one photo, but stack 50 or 100 photos, and suddenly it pops out. It's like hearing lots of people whispering the same thing. Eventually, you hear it clearly.
That's a great analogy. Is there a quicker way to just get rid of really obvious bad pixels, like those hot pixels?
Yeah, a technique called median filtering can help. It looks at a pixel and its immediate neighbors, sorts their brightness values, and picks the middle value. This often gets rid of extreme highs or lows, like a hot pixel.
Okay, cool. So calibration and stacking are key for better images. Let's talk specific targets now. The moon seems like the obvious first choice, right? Big and bright.
Definitely the easiest place to start. It's so bright you can sometimes get okay shots handheld, especially through a telescope eyepiece with very short exposures, like fractions of a second.
But what about that shimmering? The atmosphere makes it look wavy sometimes.
Yeah, atmospheric jitter or seeing, that's a big challenge. A common trick is actually to shoot video of the moon, maybe at 60 frames per second.
Video? Why video?
Because then you can use software, something like Auto Stacker, to analyze the video, pick out only the sharpest individual frames when the air was momentarily steady, and stack just those best frames.
Whoa, clever. So you freeze the moments of good seeing. What about planets? They look so tiny. Is that even possible with a phone?
It's harder, for sure. They're small, and that atmospheric twinkling scintillation really affects them. But yes, it's possible, especially with a telescope.
Same technique. Video stacking.
Pretty much, yeah. High frame rate video through the telescope, then stack the best frames. People have definitely captured Jupiter's bands and moons, Saturn's rings, even phases of Venus this way with smartphones.
That's amazing. Okay, now for the really faint stuff. Nebulae, galaxies, clusters, deep sky objects. That sounds like a real stretch for a phone.
It is more challenging, yes.
Yeah.
You absolutely need longer exposures, and stacking becomes essential because they're so faint.
Where should we start with those? Star clusters.
Open clusters are good targets. Things like the Pleiades, the Seven Sisters, or the Hyades and Taurus. They're relatively bright and spread out, so they fit nicely in the view, especially with binoculars or a small telescope.
And globular clusters, those tight balls of stars.
You can capture them, but resolving individual stars in the core is tough without a decent-sized telescope. There's always that trade-off, between the telescope's light-gathering power, its aperture, and how wide a patch of sky you can see, the field of view.
Right. What about nebulae, those gas clouds?
The Orion Nebula M42 is the classic beginner target. It's bright enough to show some detail even in relatively short, stacked exposures, even with smaller scopes.
And for fainter ones?
You need more exposure time, more stacking, good calibration. And if you're in a light-polluted area, using special filters can really help.
Light pollution filters. How do they work?
They block specific wavelengths of light that common streetlights emit, like sodium or mercury vapor lamps, but they let through the wavelengths emitted by nebulae, often hydrogen alpha and Augustin III light. Makes the nebula stand out against the background glow.
Okay. And galaxies. Can you really photograph, say, Andromeda with a phone?
It's tough. Probably the most demanding target. You need long exposures, lots of stacking, careful calibration. Everything has to be right to pull out that faint spiral structure against the dark sky. But people are doing it.
Wow. Okay, galaxies are the final boss, maybe? What about our star, the sun? Can we point our phones at that?
Whoa, hang on. Absolutely critical warning here. Never, ever point an unfiltered camera or your eyes directly at the sun. Not even for a second. The intense light will cause permanent damage. It can literally fry the camera sensor.
Okay, loud and clear, no direct sun shots, so how can it be done safely?
Only with a proper certified solar filter, one that's designed specifically for telescopes or cameras and blocks something like 99.999% of the sun's light and harmful radiation.
And this filter goes over the front of the telescope or lens?
Yes, always over the main opening before the light even enters the instrument. With a proper filter, you can safely photograph things like sunspots or prominences if you have a specialized solar telescope, even the sun's grainy texture.
What about eclipses? Solar eclipses?
Same rule applies. You need the filter on for all the partial phases.
Yeah.
The only time it's safe to look or photograph without a filter is during the brief moments of totality in a total solar eclipse, when the moon completely covers the sun's bright disk.
Right. But lunar eclipses are fine.
Totally fine, yeah. The moon is just passing through Earth's shadow. It's not emitting dangerous light. You can photograph those easily with no filter.
Good distinction. Okay, shifting gears. What about things moving across the sky, like the International Space Station or all those Starlink satellites?
Yep, you can capture those too. Usually as bright streaks. You'll need the phone on a tripod again. An exposure of around 10 seconds usually works well to show the trail.
How do you know when they'll pass over?
There are websites and apps for that. Heavensabove.com is a classic, really good resource. It gives you predictions for ISS passes, Starlinks, other bright satellites, all tailored to your location.
Cool. Now, Starlink. I've heard astronomers aren't always thrilled about those constellations. Why is that?
Well, the main issue is just the sheer number of them. There are thousands now, and plans for tens of thousands more. They reflect sunlight, and they can create lots of bright streaks across astronomical images, especially long exposures taken for research.
So they interfere with the science?
They can, yeah. They can photobomb sensitive observations, make it harder to study faint objects. SpaceX is working on making them less reflective, painting them darker, orienting them differently, but it's still an ongoing concern for the astronomy community.
Interesting balance there between technology goals. Okay, what about nature's light show, the aurora borealis, northern lights? Can phones capture that? The picture on our cover looks amazing.
Oh, yeah, definitely. Modern smartphones are surprisingly good at capturing auroras. Those amazing colors, the greens from oxygen, blues and purples from nitrogen, sometimes reds higher up, they show up really well.
What do you need for that? Just be in the right place.
Pretty much. You need to be somewhere with high geomagnetic activity, which you can track using things like the KP index. Websites like spaceweatherlive.com give forecasts. Then it's just tripod, point north usually, and experiment with exposures, maybe 5 to 15 seconds.
Wow. So seeing and photographing the aurora is actually quite achievable. Anything else atmospheric we might catch?
Briefly, maybe noctilucent clouds, those really high, wispy, silvery blue clouds you sometimes see in twilight, especially in summer at higher latitudes. They're made of ice crystals way up high. Phones can capture those too.
It's just incredible how much is possible. It really feels like this opens up astronomy to so many more people. And you mentioned citizen science. We can actually contribute.
Absolutely. NASA and other groups are really interested in this. There are apps like Anecdata that host projects where you can submit your phone astrophotos.
What kind of projects?
Things like tracking satellite streaks, monitoring light pollution levels by photographing the night sky, or just general smartphone astrophotography data collection. Your photos can actually help real scientific research.
That's fantastic.
And beyond formal projects, just sharing your photos online, maybe in Facebook groups dedicated to smartphone astrophotography or on FlickFun. It's a great way to learn, share tips, and just connect with other people doing the same thing.
So this whole package, smartphone, tripod, maybe binoculars or a small telescope, it really becomes a mobile observatory, doesn't it?
Exactly that. It's portable, it's capable, you can take it to dark sites easily, set it up quickly. It lets you observe and photograph the sky pretty much anywhere. It truly democratizes things.
Well, this has been incredibly insightful. Diving into smartphone astrophotography, this mobile observatory idea, it really is amazing to think how much of the universe is suddenly within reach.
It really is. So the encouragement to everyone listening is just try it. Go out there under the night sky, use some of these techniques, experiment, see what you can capture.
Yeah, absolutely. And maybe just think about this for a moment. The sheer scale, the wonder of the cosmos. It's now kind of literally in your pocket. The potential for your own discovery, maybe even contributing something small to our understanding. It's right there. So yeah, get out there, look up, and capture some of that beauty.